It's my great pleasure to present Dr. Daylan Tzompa for our next speaker. She is a doctoral assistant at the Faculty of Bioscience Engineering at Ghent University in Belgium. Her expertise includes food science, dairy science, lipid science, and animal production. Daylan Tzompa has experience in academia and in agribusiness, in the food industry, and the primary production sector in companies located in Mexico, USA, and Europe. Her research focused on food structure, food chemistry, lipidomics, dairy fat, and on valorization of insect fat in oils. Thank you, Dr. Tzompa, for accepting invitation to present today. So for the delays, floor is yours. Thank you.
Thank you very much, and I want to thank the invitation for speaking today. I'm very happy to see that this topic is starting to be in the interest of scientists because, well, I've been working in this topic almost 10 years, so it's exciting to see that more people are interested in it. So today I'm going to talk about insect lipids used as food ingredients. And my first question is, are consumers ready for insect oils? That's something that we will discuss today. So I will start giving an overview of insect oils. It has been already talked about it, so I will just go quickly over it. Then I will talk about the motivations for entomophagia in different parts and different cultures. And I will end up discussing some applications and the results of the consumer acceptance studies that have been done at my university. So I will want to start mentioning the species that are being produced in Europe. This is a statistic from 2017 from the IPIF. The IPIF is the umbrella association for the insect sector in Europe. At the time, they say that there were 6 main insect species being rare. The black sword fly and yellow mealworm are the 2 main species. Also lesser mealworm and 3 species of crickets. To my knowledge, nowadays there are, from these species, only 2 of them have lipids as fats or oils that are commercially available in Europe. Some breaking news this week, the European Union authorized the placing on the market of dry yellow mealworms. And they also specified that it should be as whole dry insect in the form of snacks or as a food ingredient. So this is very good news for the sector because it opens many possibilities. Specifically, this is for Tenebrio molitor. Before anything, I want to show how do they look like. In the left side, you see the larvae from yellow mealworm, and underneath is the oil from this insect. This is a commercial oil, and it is provided, well, it is from the brand Insects. In the right side, you see the larvae from black sword fly and the commercial fat from, this is from Protix. As you see, one is an oil, one is a fat. It is very, this is very positive because they have both of them different possibilities if they are applied in food ingredients. For instance, fat is very desirable to produce, for instance, bakery products because it gives structure. Also, I want to disclaim that the oils that I use in my studies are from these 2 companies. They kindly provided the oil and the fat, and they did not, they didn't have any influence when I designed my experiment. So, well, this has been shown already by many, by the previous 2 speakers, the fatty acid composition of black soldier fly. Here, I just want to highlight that this black soldier fly larvae fat can be considered a lauric fat due to its high content on lauric acid. And as previously mentioned, you can also change a lot. Like Christina was showing lauric acid content in black soldier fly of 43%. Here we have 48%, which is almost the same as coconut and palm kernel oil. So That means that the applications can be similar to the lauric fats that are currently, so the current applications of these lauric fats. Regarding fatty acid composition of the yellow mealworm, it is high in palmitic acids, oleic acid, and linoleic acids. And something interesting here is that we have found one omega-3 fatty acids, which is omega-3 from C18-3. That's the only one that, at least in our studies, we have found. Important to notice is that this oil is different in composition from two traditional edible oils, meaning sunflower oil and sesame oil, but it is very similar to that of rice bran oil. Yeah, so it has similar amount of palmitic acids, rice bran oil, than yellow mealworm, as oleic acid as well. So also the saturated and unsaturated fraction is comparable. In this study, what we did is, well, in this graph, I want to show the similarities of the fatty acid composition of different sources of fats and oils. This is a principal component analysis. It's a statistical analysis that we use to check natural clustering in the data. So in this study, we feed the fatty acid composition, and it gives us how similar or different are the samples in between them. And we can see that the insect oils have a fatty acid composition that is between that of vegetable oils and animal fats. The reason is because the insect oils are high in palmitic acid, and also oleic acid is present there. Moreover, some omega-3 fatty acids are there. In contrast with animal fats, well, it's a bit more saturated and less omega-3 and polyunsaturated fatty acids. I just added something on sterols because of this question before. So what about sterols? This is a recent study from 2021. The first reference is this one, lipidum of cricket species used as food. Not very good news, I will say, because the amount of cholesterol in this insect species, well, this study was only on crickets, and we studied 4 different species, rare under the same conditions. So the difference between them are only due to genetic variability. Sorry, it's a genetic factor. So what we found is that it has a very, very high amount of cholesterol in it. If you compare it with traditional sources of cholesterol like milk fat or eggs, is at least 2.5 times more, which is not positive. This is contrasting all previous data on insects, where they found like a very low amount of cholesterol. Several reasons, yeah, we can talk about. There are different species, so that's one option, one reason why this can be so different. But the other reason can be how are they being rare. The insects from the study from Expo were collected in the wild, while the crickets that we use are rare inside facilities with feed, commercial feed. So that can be also one option. We are now currently working on how to decrease this cholesterol level. And sorry, also just want to mention, someone also asked about phospholipids. In this paper, we are also profiling the phospholipids in the crickets. And I'm now working on yellow mealworm and black soldier fly. So probably by the end of the year, there will be a paper published on that. Some physical properties of these oils. Well, these are different types of oil: yellow mealworm, lesser mealworm, cricket, and cockroach. It has been presented before. I just want to mention that the color of the oil is very dependent on how is it extracted. So here we see oil from yellow mealworm. This is my oil that I extracted, and this is an oil that is the same species, just a different extraction. And what you see is that there is a browning on it. The mechanism hasn't been studied yet, so we do not know what is causing that. It is for sure not by air reaction, because at least the extraction that I do is always done at 5 degrees Celsius, so there's no possibility for a Maillard reaction occurring. But what I think is that probably is the same mechanism that is causing the browning in proteins. Regarding melting point, and this is the last slide on physical properties. We have oils and we have fats. So the oils that we have is like yellow mealworm, lesser mealworm, crickets, and cockroach. Here, this is a graph of the melting profile of our fats and oils, and we see that the last melting point is very low, 5 degrees, 2 degrees, 6.6, except for house cricket, where the last melting point is at 22 degrees Celsius. So this is this one, but it is still liquid at room temperature, meaning 20 degrees Celsius. Why is this? Because we have a very big fraction of low melting at below 0 degrees Celsius. So this makes the oil liquid at room temperature. In this paper, we did not publish from black soldier fly, but I do have the profile of it, and this fat melts at around 33 degrees Celsius, which is also similar to our other lauric fats. So why should we be eating all insects? What are the motivations behind eating insects? And the question is, why shall we all be eating insects? The previous speakers already talked about that we will be too many people in this earth in some years, that it is sustainable, it can be produced in a sustainable way, and we can also get several useful products from it, from insect meals, the fat, and also chitin, but also frass, which is the manure of the insects. So there are many reasons why we should be eating insects. So did I convince you to eat insects, to start having some dishes of insects in your food? Probably some of them, healthiness and sustainability will be a good reason to start eating insects the first time, for a first experience. But of course, it is not enough to achieve a second purchase or to achieve regular consumption. And this is why we need to look into the motivations of the consumers towards entomophagia. So other people have studied this, and they show that in countries with local insect culture, the main driver for entomophagia was the taste. It is delicious, that's why they are eating it. And as a person from a country where entomophagia is part of the culture, I would say we eat it because it's tasty, not because it's healthy or because it's environmentally friendly. We also eat it because it's available. If you go to the market, you can get something. If you go to the bar, you can get snacks with your beer. And it is familiar. We are used to that, so it is a familiar food, and that's what we eat it. However, in countries where insects are not recognized as food, the drivers are different. Curiosity is one of them. Yeah, the healthiness is also a driver, and sustainability. So these drive a first experience, but they are not enough to achieve regular consumption. It has also been studied that reducing visibility increases consumer acceptance, as well as meeting the expectations. So if we meet the expectations of the consumers, then we will achieve regular consumption or a second purchase. But what is meeting expectations? So the consumer understands by meeting expectation that it has to be a familiar product. The insect-based food has to be in a product with a like flavor and a like preparation. The product has also need to be appropriate. That means that they need to think that, okay, the insect in that dish is correct. And sometimes it's not the case, hasn't been the case. And the far most important driver is the taste. It needs to be good. So from these previous studies, we learned, we took that knowledge when we decided our research strategy. So the first thing that we included was to reduce visibility in the insects by using oil as an ingredient. We produce familiar foods, and we decided to go to bakery products because bakery products are familiar in Western countries. We also tested for appropriateness in terms of flavor. So if the flavor from the oil is appropriate for certain dishes. And the most important thing for us is taste. We are developing products that are tasty. And I will come to this back later. So now I will discuss some of the applications of our studies and the results. And the first study that we made was using black soldier fly larvae fat. And we used this fat in 3 different bakery products. That was pound cake, sand cookies, and waffles. So in the study goes about replacing butter in these products at different levels. In the trials, we went until 100% of substitution. However, we noticed a very strong aftertaste that was coming from the insect fat. For this reason, we decided to substitute only until 50% for the final experiment with the consumers. Why? Because we do not want to give a bad first experience to the consumer. This will give them a bad experience, and it will hinder the consumption of insect-based foods in the future. Even if it's a different ingredient, if it's in a different situation, they will relate it to that first bad experience. That's why we went only until 50%, where we decided, okay, this is a safe level where most of the consumers will not perceive it so strong. The results show that we could go until 50% of butter substitution in waffles without changing the consumer preference or the sensorial perception. At higher levels of substitution, we, as I mentioned, we had of flavors. This was the case for the waffles, but for cookies and cakes, we could only get until 25% of substitution. At higher levels, the consumers perceive it already. Very interesting, no change in physical properties of the product, not even when we replace it 100%. That means that the black soldier fly larvae fat is giving functionality. There are no defects on the cake. And for instance, which defects can you have? One typical will be oiling off, so that the oil is coming out from your product, and that will be considered a defect. That's very positive. Something also good to notice is that, well, interesting from the scientific point of view, is that why do we have 2 different behaviors between the 2 products? And what we think it happened is that there is a difference on how these products are produced. Cakes and cookies are produced in a convection oven, while waffles was in a heating plate, where the dynamics of releasing flavors and volatile compounds is different. So there will be a higher rate in the waffles as compared with the cookies, because the temperature inside the product will be increased. So this gave us the idea for a second study. In this case, we used oil from yellow mealworm, and we deodorized this oil first to reduce the volatile compounds and the aroma. Some aftertaste will be reduced. And we tested in 2 different matrices to test the the appropriateness of the flavor. Yeah, so the results show that we can get until 100% of substitution without decreasing consumer preference. Also, these cookies, the cookies with deodorized insect oil were preferred. This was the story for the crackers, but in the hummus, it was not appropriate. So that means that all the preferred product was that with vegetable oil, 100%, and in all the products, there was an aftertaste. So they think that was not appropriate because there was a very typical flavor from the oil that was not appreciated by the consumers. In the later study that we're working on the publication, we use this oil to fry products and fry doughs specifically. So we produce donuts. Also, we use deodorized insects oil. And we found out that indeed also we can get until 100% of substitution. So 100%, the donuts fried in 100% insect oil. Without changing consumer perception, and even the donuts with 100% vegetable oil were the least preferred. So something very interesting. The conclusions is that the flavor profile of insect lipids affects the food preference, sometimes in a positive way, sometimes in a negative way. These insect lipids require a prior refining if we are going to use them as food ingredients. The authorization is necessary, and the consumer developers should consider the flavor appropriateness. My take-home message: insect oils are different from vegetable oils and animal fats. Regular consumption is it can be achieved if we take into account the different factors that were discussed today, and we can achieve substitution of traditional fats and oils with insect fats if these oils are refined. Also very important, we need to take into account if the flavor of the oil is appropriate for the product. I just finally want to thank my colleagues from the Agricultural Economics Department, which are also involved in this project, and Professor Kundeveting. Thank you very much.
Thank you, Dr. Tzompa, for the wonderful presentation and covering even some of the questions that we had in the chat. Let's see what questions we have. So we have a few minutes for the question before we all join for the panel discussion. Can you say, the question is, can you say something about blanching the black soldier fly larva to prevent browning during the drying process or other processing steps? I think it's more related to oil processing, but I think you already received the oil, right?
Yes, yes, indeed. In the beginning, I thought I worked with the extraction, but I never blanch, so I do not know. I know that this browning in protein is an enzymatic browning, so blanching can stop the activity of this enzyme. So it could be positive for the oil, no browning, basically.
Have you determined free fatty acids amount versus triglycerides to understand refining yield losses? So from crude crude insect fat to deodorized, how much free fatty acids versus triglycerides?
Yes, before doing the authorization, we did all the type of tests that are necessary. The oil that we get from insect is very good, actually. It was a very low acid value, almost no difference before and after. So that means that it's also very stable. And I think there are antioxidants present in the oil. Probably they will also add some antioxidants, but the oil that I got was not antioxidants. And also very low in peroxide value, in acid value, and all the parameters. Yeah.
Sounds good.
But that depends, of course, in the extraction. How do you extract your fat?
Okay, I have difficulties. Oh, okay. The next question was, as a process for separating oils and fats well developed, easy for industrialization?
Yes, and it's already present. There are also companies that are already selling these equipment for separation, and they valorize the pellets, they get the oil, and I think even the chitin, some of them. And what I know is that they are using tricanters.
Okay, and just one more question. Somehow it's not moving in my... I cannot see the questions.
I see one that says, apart from diet, what other strategies do you intend to use to reduce those elevated cholesterol? Industrially, you can eliminate cholesterol by beta-cyclodextrin. That's a process that is already available for other products like egg yolk. we are now doing some changes on the environmental setups. But I cannot say a lot because just the tests are now running. Hopefully by the end of the summer, we will have information on that.
Sounds good. So then there was question on for after test. Let's have just one more question, and then we will move to the panel. So for the aftertaste or volatile, if 100% fat used in baked product, do you know what minor components in the fats oils are responsible for this? So for off flavor.
For black soda fly, we didn't make the deodorization. I only had the opportunity to work with that 1 year. We didn't make the deodorization, so I do not really know. I know that the lauric fats, they have themselves a very strong flavor. So you taste coconut oil, that's and the people refer that aftertaste from the black soldier fly being the taste of the lauric fat. So, but that's something that needs to be studied yet. And for yellow mealworm, I make the deodorization, and also I'm working on the paper on that. And in that paper, we did extracted the during deodorization. What you do is you heat the oil under vacuum. So whatever you extract is condensed afterwards. And we got the condensation of that one, and that's what we studied also to check the compounds there. So, but I do not have the name of the compounds in my head now. I'm very sorry for that. But if you give me the email, I will send I can send the chart with the compounds present.
Sounds good. Sounds good. Thank you. Thank you, Dr. Tzompa, for presentation and answering the questions.